We are studying adhesive interfaces in semiconductor packages. Adhesion is a technology that has been used for more than 5,000 years, but its mechanism is still largely unknown and subject to debate. Even in electronics, there are very few examples of theoretical chemical studies of adhesive interfaces, so additional clarification is desired. In this paper, we examine the interface between gold and the epoxy conductive adhesive of the die bonding structure for LEDs, both theoretically and experimentally. We clarify not only the ideal adhesive structure and theoretical adhesive strengths, but also consider the differences from the actual adhesive structure. The theoretical structure was obtained through first principles calculations. Using a technique called density functional theory, we molecularly modeled the adhesive interface between gold and epoxy and searched for the most energetically stable structure. We also calculated the theoretical adhesion force from the energy required to pull off molecules adsorbed on the gold surface. At the same time, regarding evaluation of the actual adhesive structure, in addition to measuring the shear bond strength using the rupture test, we studied the factors that affect adhesive interaction by analyzing the dipole surface in detail. As a result of our research, we found that there may be a difference at the molecular level in the adhesive interaction between the ideal and real interfaces. It turns out that in the ideal structure, the functional group derived from the epoxy hardener can form a chemical bond with the gold surface called a sigma bond. On the other hand, under actual adhesion, it was presumed that the altered layer on the gold-plated surface had an effect, changing to a mechanism based on hydrogen bonding. Molecular studies of such adhesive interactions can be applied to improve product quality. For example, the adhesive interface between gold and epoxy is a structure found in many semiconductor packages. In optical devices, it is used for lead frames and connections between substrates and semiconductor chips. If this bond delaminates, the device will not work, so the reliability of the bond must be ensured over time. In this way, we hope to increase the adhesive reliability of packages. Adhesive reliability design is a technology for guaranteeing stable device operation, so to speak. Ensuring that devices do not fail and continue to perform as expected is fundamental to the safety of the system. We hope that ROHM's quality-first products will achieve safe and secure electronics that support people's lives in various fields such as communication and power. Similar research is being conducted in the field of power systems that handle large amounts of power. Adhesion is used extensively not only in discrete components but also module products. For example, the adhesive interface between the copper lead frame and mold resin is a critical structure used in many products. We will continue our research with the aim of establishing adhesive technology that can be used safely even in harsh environments.